That's a great start. Thank you, Forrest. I've got something special for you today. It's called Blade, and it's a proof of concept graphics library I've been working on. Why another graphics library, you may ask? There's so many already. There's Vulkan, there's GFX, Luminance, Sierra, RAFX. WGPU is, I think, used by most projects today, and it's hugely successful. Why do you need another one? Is the game they have not done yet? Can we finally start making games and not graphics libraries and not engine? So yes, this is all right. We have a good landscape. Libraries are great. They reach the level of maturity, and I'm very happy with the WGPU ecosystem in the way it is present today. However, I think the picture is not complete until we explore the design space for graphics libraries completely. And I found one area where we don't have anything yet. And I tried to build a prototype library based on this idea. And I will tell more as we go. It's called Blade. It's just a graphics library. The main motivator for this is my pet project, Rust Avengers. It's a render and a re-implementation of the old game. I talked about it a few times. We should show you've seen the screenshots. It has a lot of rendering. It has a lot of compute. It's full of experiments on how do we have different ways of rendering the terrain. I have like 6 different ways of rendering, entirely different. There's a lot of pipelines lying around, a lot of line group layouts defined. And I found experimentation on Avengers to be less ideal. And I thought maybe we can do better than this. It must be fun to experiment. I don't want to be dragged down by boilerplate where I don't care about it. Today, it has like 15 pipelines with 7 layouts. And before, when I had the GPU physics implemented, it had maybe twice as many. It has a lot of stuff in it. And we also see a big picture on for the last maybe 20 years or something, that you could move more and more computation on the GPU side. This a while ago, there was the approaching zero driver overhead paper showing how in OpenGL you can submit draw calls on GPU and do everything on GPU. And today we have a lot of compute happening and machine learning. And of course, one big area is ray tracing. It's really hard to find an example where you wouldn't want to do most things on GPU. To me, the only extreme example that comes to mind is GTA 5. If you're doing something like that, maybe you don't want to do most things on GPU. Otherwise, for example, in Avengers, once I had more than a trivial number of cars rendering, I figured that I would just use batching and do instance rendering. And with this, the number of draw calls reduced significantly. So wherever I went, there was always a way to have a low number of draw calls and a low CPU overhead for them. It's all about GPU. So a very important question is, why didn't I just evolve WGPU in the way that I want? And a simple answer is constraints. The WGPU as the top level library is constrained by the fact that it's a part of the Firefox. It has to run on many backends, and it's somewhat difficult to. It's not as fun to hack on because there is still a few layers down the ground. It's also safe. While for my cases, I thought it would be good to have something if you know what you're doing. So for most cases today, for most user applications, WGPU is absolutely the right choice. But I thought there's still a few cases where I know for sure how to debug on native APIs. I know how to implement it. So I just need more ergonomics, and I need to be closer to the metal. So what about the WGPU HAL? I did try to evolve HAL in the direction that I was thinking. Like I made a PR that made HAL objects copyable, and that's copyable objects is something very silly, but it's super convenient in terms of ergonomic. Just being able to put your handle to a buffer somewhere without caring about the fact that it's a unique handle makes your life much easier. So it turned out that I can't really evolve WGPU HAL in this direction. Moreover, it supports more backends than I currently care about, and these backends carry the limitations on their own. In particular, D3.12 is very constrained. So let's think about this question. Programming is all about managing complexity. Where does the complexity live in these libraries, in the full stack of those libraries? And I made this chart, which is a little bit silly. Don't take it literally. But the main idea is, in case of WGPU, all the complexity is managed by the library itself. So, well, most of the complexity, sorry. The part on the right, the red part, which is the user, is where the user defining the layouts for things. And WGPU has a way for layouts to be derived, but you still need to create define groups and manage them. And most things happen inside the library. The library tracks all the resources, validates and inserts the transitions. So this is where it lives. In WGPU HAL, it's completely zero. Library doesn't do anything. And that's the point of WGPU HAL, is that you as the user decide how to use the GPU. But it's not ergonomic at all. Writing for WGPU HAL manually is a little bit involved. It's not as involved as Vulkan, but it's still involved. In Vulkan, it's kind of hard because I don't know very well. I think a lot of complexity is managed by the type system, but I don't know exactly how much. It's still a very low-level API. It's basically Vulkan. So I put user as a dominant factor. And finally, Blade. You see, Blade is very different according to this metric, because it is trying to make the driver do all the work, not the user, not the library. The library is super thin. It's basically very, very pass-through. The user gets a very ergonomic API, and the complexity is managed by the driver. How do we do this? Let's start with the state tracking. That's one of the important bits. In other low-level APIs, you care about the access for resources, and you care about image layouts. And you transition images between layouts. You want to render to a render target, you transition it to the render target optimal, you render it, and you transition it back to the sample, and so forth. These transitions are encoded and validated by your Vulkan implementation, and you have to take them into account when writing code. And WGPU mostly handles that for you. Mostly because you can still get in a situation where you're doing something invalid, and it will tell you. In Blade, there is no pure object state at all. And this is achievable because Vulkan has a general image layout, which can be used for everything. And the same for Metal and the same for OpenGL API. With the general layout, you don't actually need to transition the layout, but you still need to transition the access to the resource. And for this, Blade uses global transitions only. So there is no pure object image layout. There is no pure object access patterns. There is no pure object anything. You just write passes like here. where the pass ends, there is a global barrier. That's it. So as an outcome, you would think that this is maybe not the most efficient on GPU, but evidence suggests otherwise. In terms of the global barriers, I'm talking about cases where you do most things on GPUs anyway, so you don't have a huge number of passes, and and a few barriers between the passes do not contribute to anything. You will not see it on your profile significantly. In terms of the image layout, the fact that I'm not using the optimal layouts for any operation is only matters for a few GPUs. And today the industry seems to be leaning toward an approach where it doesn't matter at all. It's a big surprise, but again, I'm talking to you on the laptop with 6850U AMD APU. This is one of the latest models of AMD APUs, and running a benchmark of Blade basically becomes GPU limited, the same as WGPU, even though Blade doesn't care to set the render target optimal layout. So this means that modern GPUs and drivers, they either don't care or they have the hardware to actually compensate by the fact that you are not in the right image layout. So in the end, it doesn't matter that much. And maybe we don't need to pay that. So with Blade, I'm trying to explore this area where most of the work is done by the driver itself, and the driver will know what is important and what is not.
Sorry, Clark, just to interrupt quickly. The message you are streaming to the screen is visible, and it's just occluding some of the stuff.
Whoa, okay.
Perfect.
Okay, thank you. Yeah, so ergonomics of this is very simple. You create a resource, you use it, you submit the command encoder. That's it. You don't care about transitions. The only one tiny single bit you care is initialize image thing, because you need to transition from an initialized layout to the general layout. So a one-time encoder operation for any texture that you create. That's all. Then we go to another big thing, the binding model. It's arguably one of the biggest differentiation factors between the low-level APIs, and that's what WebGPU group spent ages discussing on how to do it properly. WebGPU ended up with the Vulkan-like binding model, and that's probably the biggest differentiation factor between WebGPU and Metal today, that it uses the Vulkan binding model. In Vulkan binding model, you create a descriptor set layout, and then you create a pipeline layout. And then when creating a pipeline, you give it a pipeline layout, and then you just allocate descriptor sets as if you're allocating memory, and you bind those descriptor sets. And it's a lot of work. It's most work you're doing, most boilerplate you're doing in your code. And this binding model management in Avengers, Trust Avengers, is taking a lot of code, which I don't think it's valuable. So in Blade, you don't have any of that. You don't have layouts, no bind group layouts, no descriptor set layouts, no pipeline layouts, and no sets either. It's magic. You don't need descriptor sets. It turns out you can just create your pipeline and bind your data. Everything else is handled by the driver. And on top of that, the cherry on top is that there is no uniform buffers. If you are drawing something, you need some data, you just pass this data in directly. That's it. You don't care how it gets to the GPU. You don't care about whether push constants are available and what is the size of them. How to manage your uniform buffers, how to circulate them, how to prepare them before the render pass, because you can't do transfers inside the render pass. All that boilerplate, all that headache goes away. You want to render something, you just say, I want to bind this struct, and it has some plain data in it. That's it. Like here, This is how you define those structs. Foo is effectively a bind group, but you don't need the layout. You just derive the shader data for it. It contains a texture and a uniform buffer. Where the uniform buffer should be, you just provide the byte mock, the plain old data structure. That's all. When creating a pipeline, you give it the layout derived from this shader data struct. The syntax here is a little bit unfortunate that you have to do foo as shader data, but I think it's bearable. Every pipeline in Blade has its own layout, and this goes across those Vulkan folks who specifically want to share the resource layout between pipelines. Well, guess what? D3.12 doesn't have that at all. In D3.12, you basically have a new layout for every pipeline at the API level, not even at the driver level, but at the API level. So it's a strong evidence that maybe sharing resources between pipelines is not really that important. And if you're not doing this, the binding model simplifies significantly. If every pipeline has its own pipeline layout, implementation becomes simpler. Like I can do OpenGL backend with way less code than WGPU HAL because I don't want to share data between pipelines. It's all contained. This is how you bind it for drawing. You just say my bind group 0 gets this structure. That's all. And another funny thing you may see is that my texture view here is an actual texture view. It's a Blade texture view. It's passed by copy, not by reference, but by copy. And this is because all the object handles, like resource handles, are copyable and they're designed to be small. They're just a few machine words of data. So they're designed so that you're able to just pass them around as needed. You can create hash maps of them. You can just pass them in functions, anything. Writing for this model is really, really ergonomic. It's making things so much more enjoyable for me to write. So I'm looking forward to build more things in it. I have a few examples right now, which I will show. But the ergonomics part is achieved in this proof of concept library. And I even would go as far as to suggest that maybe WebGPU should have done the same for the binding model. Because it's not like you're going to build GTA 5 on WebGPU either. So there's other constraints in place, and making it simpler would definitely benefit it in the long run. Maybe there is still something to consider. Oh, those of you with the low-level background may wonder how this is all working. Like, why do I not need the uniform buffers or descriptor sets, or especially on Vulkan? So Vulkan has a few things to help. I'm still prototyping. I'm still not completely sure where I'm going to settle, but it has the tools to implement this. The thing that's used in the published crate right now, and it is published as of a few days ago, is using inline uniform block and associating every command encoder with a descriptor pool. So if you bind something, you have a descriptor pool. It just allocates the descriptor for you and binds it instantly. You don't see that. And the uniform data is inlined in the descriptor itself. So this is, for the driver, it makes it very convenient. And when you reset your command encoder, the descriptor pool is also reset. So the lifetime is very clear. There's no confusion for the driver or for you on what the lifetime is. And you can bind a lot of things this way. I was surprised to know how much stuff you can bind per frame without slowing down on CPU. The other thing that Vulkan can do is to push descriptor sets, but I had a few problems with this, but I'm still considering this on the table. All right, so this simplification allows there to be very, very little code. This comparison is completely unfair. Like, don't use it anywhere. Completely unfair because RAFX and WGPU are way more mature. They have a lot of things in them, good logic that is required. But in Blade is just a proof of concept. Right now, I see that it has twice as few the lines of code for Vulkan and Metal than other libraries, and OpenGL is even less. So all of the backends are within something like 2,000 lines of code. That is absolutely nothing. It's super, super simple inside. Very easy to debug and reason about. Yeah, with all those shortcuts, with the resource states and bind groups on the fly, how can I do draw calls? I mean, I could say that maybe you don't. Maybe the applications you write in Blade just don't do a lot of draw calls, and that would be fine. As I said, it's not for GTA 5 kind of scenario. But so far from what I measured, it's actually very fast. I can do on an old MacBook Pro, I can do 20,000 draw calls with a unique descriptor set each per frame for 60 frames per second. I think that's enough, right? How many of your games do more than 20K draw calls? Right. So on this laptop that I'm talking to you right now, the benchmark goes into 50K draw calls, and it's still not CPU limited. It becomes GPU limited for both WebGPU, WGPU, and Blade. So basically, it's fast. Now, Blade is a lean and mean library. And we talked about the lean part. What about the mean part? It's totally unsafe. Yeah. Again, the idea is you know what you're doing. You know the APIs you're targeting. You can use the GPU tools, the validation layers. It does help you enable them, but you know how to read them. And this is basically what I do for myself. I do know how to read them, and I want to be in control. So it is unsafe. It's as I said, there's no tools involved, and it is incomplete too. It's a proof of concept so far. For example, I have only a few texture formats right now. I don't have any vertex buffers. Who needs them anyway? You can just bind the buffer and index it with your vertex ID. So there is one object responsible for the context that contains your queue and device and everything, and it's internally synchronized. This is also a big experiment in the workflow scenario. All the libraries I made before, there's sort of implicit expectation that I'm going to maintain them and fix them. Here, I'm honestly, I cannot provide that. I admit I cannot allocate time to maintain it like all the other libraries. And I direly recommend everybody to read what it feels like to be an open source maintainer article. It's enlightening, and I relate to this so much. It talks about the life of a maintainer and what a day looks like, basically, for a maintainer. So here, I want to try a different model. As you see, Blade tries to be very different from other libraries. So it's also about the workflow of development. I'm going to try the model where you take it and you customize it for your needs. Like you're making a game, let's say Avengers or Valorant or any other game, basically, and you need a graphics stack, you need some backends, right? So you just take Blade, you put things in it that you need. Maybe you come back to upstream and suggest and do pull requests. Maybe not. Up to you. So this is very mean. I'm sorry about this, but that's the only I can do in my situation right now. I mentioned before that objects are copyable. This is what the buffer looks like in Vulkan. It's basically 3 machine words. You can copy it around. Now the context, the global context, I call it global. It's still an object, but it's an internally synchronized object. Like you create resources, you submit your command buffers. It's all you take it immutably, so you can put it in an arc and share it if you need. It's very convenient, and also it does kind of abstract well, because on Vulkan the device is internally synchronized, the queue is not, and on Metal everything is not internally synchronized. So I know where to do lock-in and where I shouldn't do lock-in, and this is a part of the implementation. You don't care about this. You just consider everything internally synchronized. This is a thing we can't get around. We need shaders. So for Blade, I'm using the state-of-art shaders, which is Wigzell shaders, which is a web GPU shading language. But it has a nice, it has a very nice property here. Because as you know, in Wigzell, you generally annotate your resources with binding and groups. You know where in the pipeline layout your resource should be. So in Blade, you don't. There's no pipeline layout. You just declare resources. That's it. Like, I need a sampler. I declare a sampler. This is one of my favorite parts. It's matched by name on the Rust side. So your fields of the struct that you're providing for the shader data match by name with the variables, the global variables in your Wigzell modules. And this is how binding is done. So the nice part about it is that writing shaders, you don't care about the layout. Just declare what you use, and that's it. The hidden nice bit is that it's actually almost a valid Wigzell module, almost in a sense that you can use Naga to validate it today. I added a flag to Naga that allows validation without the binding decorations. So you get complete tool support for your shaders. You get complete validation. You can make sure that they work. And yet, when you instantiate the shader for the pipeline, it will build the pipeline layout and actually inject the Naga module decorations in the modules that it loaded. So everything is handled for you. Oh no, this slide is too big. We don't see it, right? Yeah, so going closer to the conclusion, why would we use Blade? You use Blade because it has great ergonomics story. It's made for ergonomics. I would say if you're building an unsafe library and you can't basically limit the unsafeness, at least make it ergonomic. This is what Blade does. It has very simple synchronization model, very simple binding model. It has true Wigzell shaders. It's lightweight. And let's see if it lets me. Oh, it doesn't even let me see the thing. Okay. Yeah. Okay. Okay, what happened? Did I lose it? Yeah, that's better. And all the objects are copyable. You can move them around, and it has a context that's convenient to use. These are the reasons to use it. Reasons not to use it is that it's very incomplete. It's not going to be actively maintained, in a sense that I'm going to maintain it for my needs. And if you have something you want to add, I will consider that adding upstream. And if you are not entirely sure what you're doing, then you shouldn't be using Blade. All right, let's run some demos here. So this is the benchmarking example I used, where you spawn a bunch of bunnies. It becomes slow here very early because it's in debug and we are actually streaming. But in release without streaming, I reach 50K bunnies and become GPU limited. It tests, every bunny is drawn with its own bind group or descriptor set. So it tests the binding capabilities. It's not instanced in the way you would be doing this in a real game. Again, no validation errors. It's running on Vulkan in this case. This is a particle system. And as you can see, I have a eGUI integrated. So eGUI integration is like really, really simple because the binding model is so simple. You can tweak some parameters. This is doing a GPU simulation of particles in compute shaders. It is doing instancing, and there's like 20 or 200,000 particles. There's a lot of particles, basically. That's what you would do on GPU particle system. Also, there is a thing I should show you as well, which is important. Okay. Yeah. The backends I have are Vulkan, Metal, and OpenGL ES, mostly for the web. So here I'm running the run WASM on my machine so that it can create a local host. I can open it here. Okay, see? So we just built for the web and ran the same demo on OpenGL ES3, and it runs. There's very little code there. It seems to work so far. So here we are. The repo is now public. Again, it's a very different library from what I used to do. And it's a big proof of concept. And I'm excited about the ergonomics of it. And I want to try it in more contexts. That's all. Thank you for listening.
Awesome. That's super cool to see more progress in the graphics API space. Of course, as soon as I start talking, my dog starts barking. So, got a few questions here from the Discord. I put the Discord link in the YouTube chat. If anyone on the stream wants to join, I will also copy that over to Twitch chat in a second. So from Noxum, if the core ideas are that the low-level APIs are not required for if the core ideas are that low-level APIs are not required for performance and user space state tracking has ergonomics overhead, what does Blade bring to the table over existing cross-platform APIs like WebGL?
I think the question is formulated a little bit incorrectly. I'll try to answer the last part of the question. So what does it give you on top of the WebGL? That's the question. OpenGL is deprecated on all platforms today. I know that it's controversial, but on Linux, all the vendors only want Vulkan. On Android, all the vendors want Vulkan. If you run an OpenGL application, they want you to basically run through a layer that translates it to Vulkan anyway. So on Linux, OpenGL is legacy. On D3D, OpenGL has always been legacy. On macOS, it's been legacy as of, 3 years ago? And now I don't recommend you running anything. So I don't think it's a good choice. And Blade is going to be much faster than OpenGL because it still uses a better model for the interaction. You still have passes, the concept of passes. You still have the concept of pipelines. There is still bind groups involved under the hood. So I think you would get a better outcome with Blade. Yeah.
Cool. I think I'm getting some issues with posting the Discord link due to spam filter, so I'm looking at getting that solved. Yeah, let's see if there's anything else in here. I really like the idea of having everything just be immediately bound. I'm kind of curious, how do you deal with those sort of large scale buffers that you do with like any kind of GPU powered anything where you have, how would you say bind your Vertex buffer without uploading it every time?
Right. Only the uniform data is inlined. You can bind the storage buffer like a buffer.
I see.
Yeah.
All right, that makes sense. Yeah, unless anyone else has anything else, I think we are ready to go. And in a minute, we will get back to the next talk, implementing an extensible renderer.